We only know a tiny part of the cosmos, and our knowledge comes from powerful and sometimes enormous telescopes that allow us to observe and study the universe. With telescopes, we collect electromagnetic waves such as visible light and many other frequencies from objects near and far. We obtain wonderful images of exotic and fascinating objects, but above all, we learn about the details of the history and evolution not only of our solar system but also of the vast universe in which we find ourselves. Today, there are hundreds of telescopes capable of studying the universe, active on Earth and in space, some of which are truly unknown. There are also many projects to build new ones, bigger, more powerful, more cutting-edge. Many of these are being built because we want to observe at different wavelengths and because, as technology progresses, we develop increasingly sensitive and high-resolution instruments to do so. In this video, we will see what are the largest and most ambitious telescopes currently under development, and we will also see why they were designed, who is building them, and what they will focus on. Let's start with a small but necessary introduction. What does a telescope do? Briefly, it collects light, i.e., electromagnetic waves from the universe. These can come from the sun, from planets, thus always light reflected from the sun, or from outside our solar system, where the sources can be all kinds, from other stars to phenomena like supernovae. There are also many other sources that in turn reflect light, such as dust and gas clouds. In all this chaos of different sources, we now open another small parenthesis. The radiation we receive is only a tiny part of the visible light from the universe. Indeed, we receive electromagnetic waves of different wavelengths, from radio waves to gamma rays. By studying different waves, i.e., different wavelengths, we can observe different phenomena or understand different things about the same phenomenon. Sometimes, moreover, different telescopes cannot observe with the same precision or scope large portions of the electromagnetic spectrum, and therefore to observe further or more precisely we build telescopes that are suitable for observing in more or less narrow portions of the spectrum. An example is the most famous space telescope currently active, the James Webb Space Telescope, which mainly observes, but not only, at the infrared wavelength. Now that we have made this introduction, we will see 7 of the main telescopes that we are building, both on the Earth's surface and to be carried into space. Let's start with the first ones. The telescopes built in the observatories called ground-based, i.e., located on the Earth's surface. One of the most anticipated projects is the Vera C. Rubin Observatory, currently in the final stages of its construction on the summit of Cerro Pachón in northern Chile. This observatory is named after the American astronomer Vera Rubin and will house an optical reflector telescope with a primary mirror of 8.4 meters. Thanks to an innovative and cutting-edge design, the telescope will provide sharp images over a very wide field of view of 3.5 degrees in diameter, which will be observed by a 3,200 megapixel camera, the largest digital astronomical camera ever built so far. The main scientific objective of the Rubin telescope is to conduct a decadal survey of the southern sky and, during this unprecedented campaign, it will collect and process more than 20 terabytes of data every night and up to 10 petabytes per year for 10 years. The speed and design of the telescope will allow it to survey the entire southern sky in a few nights and create a real-time time-lapse film of changes on different timescales over a decade. The camera will detect and capture images of about 30 billion stars, galaxies, stellar objects, and asteroids. The Vera C. Rubin Observatory is funded by the National Science Foundation of the U.S. Department of Energy and other private funding. Its construction began on April 14, 2015. With the laying of the first stone and should have been completed between 2022 and 2023. Currently, the first activation of the gigantic camera is scheduled for the end of this summer, i.e., 2024, while that of the entire observatory for January 2025. In August 2025, the actual scientific operations should then begin. Also in northern Chile, but in the Atacama Desert, engineers and construction workers are currently assembling the structure of the dome of a truly revolutionary telescope. It is called the Extremely Large Telescope and is being built by the ESO and will be the largest and most technically complex telescope in the world for observation in the optical and near-infrared. Its segmented primary mirror will be a whopping 39.3 meters in diameter. while the secondary mirror will have a diameter of 4.2 meters and the entire telescope will be supported by adaptive optics to correct atmospheric distortion. The observatory will collect 100 million times more light than the human eye, i.e., equivalent to 10 times more light compared to the largest existing optical telescope. Moreover, this new observatory will correct atmospheric distortion over an area approximately 250 times the light collection area of the Hubble Space Telescope and is estimated to provide images 16 times sharper than Hubble. The scientific goals of the project include detailed studies of planets around other stars, observation of the earliest galaxies in the universe, and supermassive black holes. It will also study the nature of dark matter and dark energy. Finally, it aims to detect water and organic molecules in protoplanetary disks around other stars. Construction of the ELT began in June 2014, but the cornerstone was laid only on May 26, 2017, marking the start of the main structure's construction. In July 2023, the observatory surpassed 50% of its development, and its enormous dome, standing 74 meters tall and 86 meters in diameter, is the largest ever built in the world for a telescope. Its construction has been entirely entrusted to the Italian consortium of enterprises ACE, and its completion and the start of observations are planned for 2028. We have so far discussed two large optical telescopes, but now let's move on to another type of structure. A radio telescope, and not just any, but the largest and most innovative radio telescope in history, the Square Kilometre Array, SKA. This is an intergovernmental project whose combined infrastructure, the SKA Observatory Consortium, is headquartered in the United Kingdom and was founded in Rome in March 2019 by 7 initial member countries. This international organization, which has since gathered many other countries, is tasked with building and managing this observatory. The project has 2 phases of construction: the current SKA-1, commonly simply called SKA, and a possible subsequent phase, significantly expanded, called SKA-2. The construction phase of the project began on December 5, 2022, at several sites, because SKA will be a single gigantic radio telescope, but consisting of 2 different arrays of radio telescopes. The first is called SKA-Low, at low frequency, and is under construction in Western Australia. The second will be called SKA-Mid, at medium frequency, and is being built in South Africa. Both sites were chosen in the southern hemisphere of our planet, where the view of the Milky Way is better and radio interference is minimal. Upon completion, expected around 2030, it will operate across a broad range of frequencies, and its size will make it 50 times more sensitive than any other radio instrument on Earth's surface. If built as planned, it should be able to observe the sky more than 10,000 times faster than is possible with currently used instruments. We have talked about optical, infrared, and radio light. Now let's move to high energies, and we cannot fail to mention the Cherenkov Telescope Array, CTA. This is also an international project, currently involving more than 30 countries and 1,500 researchers to build a new generation of ground-based instruments for observing gamma rays, in the energy range from tens of giga-electronvolts to about 300 tera-electronvolts. In its final construction, the CTA will consist of 2 arrays of telescopes. A first series in the Northern Hemisphere, in La Palma on the Canary Islands, which will study extragalactic objects at the lowest possible energies, and a second series in the Southern Hemisphere, in Chile, which will cover the entire energy range and focus on galactic gamma-ray sources. It is expected that in total there will be more than 100 gamma-ray telescopes involved, while the current arrays host a maximum of 5. To give you an idea, these telescopes will be of 3 types. The large-sized telescope, with a diameter of 23 meters. The medium-sized telescope, with a diameter of 12 meters. And finally the small size, which have a diameter of 5 meters. Their task will be to capture the so-called Cherenkov radiation, a bluish light caused by the impact of gamma rays or cosmic rays with the Earth's atmosphere. The analysis of the data obtained from the telescopes will allow researchers to trace back to the cosmic sources of gamma rays, which can then be studied further. The INAF, the National Institute for Astrophysics, will contribute to the construction of the small telescopes at the southern site. For example, a precursor of which was the ASTRI telescope, astrophysics with Italian replicating mirror technology, a telescope funded by Italy and already active in Sicily. Now let's move into space. Because to see the cosmos with eyes unobstructed by the Earth's atmosphere, it is necessary to surpass it and position at least in Earth orbit. One can go even further for other advantages. Like at the Lagrange point L2 of the Earth-Sun system, 1.5 million kilometers from Earth, an excellent point for observing deep space. And where, for example, the James Webb Telescope is located. One of the most interesting space telescopes currently under construction is the Nancy Grace Roman Space Telescope. The next space telescope from NASA is expected to be launched aboard a SpaceX Falcon Heavy in May 2027. Named after the American astronomer Nancy Grace Roman, it will be positioned in orbit around the Lagrange point L2. The Roman will feature a primary mirror of 2.4 meters in diameter and will carry two different scientific instruments. The first, called the Wide Field Instrument, is a 3.8 megapixel multiband camera in the visible and near-infrared spectrum that provides image sharpness comparable to that achieved by the Hubble Space Telescope, but with a field of view 100 times larger. The second instrument is a coronagraph, consisting of a camera and a spectrometer with a reduced but high-contrast field of view covering both visible and near-infrared wavelengths, utilizing new technology for starlight suppression. The main scientific goals of the Roman telescope will be the search for extrasolar planets, or exoplanets. Additionally, it will study the evolution of cosmic structure and the measurement of the effects of dark energy, with this area of research also being advanced through joint observations with the Euclid Space Telescope, launched in July 2023. Scheduled for launch with an Ariane 6 rocket in 2026 is the European satellite Plato. The name also refers to the classical Greek philosopher Plato, and it will be a space telescope entirely dedicated to the study of extrasolar planets via the transit method. It will observe the brightness fluctuations of 1 million stars caused by the passage of planets between the star and the telescope and, thanks to advanced onboard instrumentation, will be able to determine the radius and mass of these exoplanets. The focus of the mission will be planets similar to Earth in the habitable zone around Sun-like stars, where water can exist in liquid form. A secondary goal of Plato is to study seismic activity in stars to measure stellar masses and their evolution, thus enabling precise characterization of the host star of the planet it discovers. In 2029, also aboard an Ariane 6, the launch of Ariel is planned, another ESA space telescope and the fourth medium-class mission for the Cosmic Vision program. Ariel will observe 1,000 planets orbiting distant stars and will conduct the first large-scale survey of the chemistry of exoplanet atmospheres. The objective is to answer fundamental questions about how planetary systems form and evolve, understand how a planet's chemistry is linked to the environment in which it forms, and how its formation and evolution are influenced by its host star. Ariel will study a diverse population of exoplanets in a wide variety of environments but will focus on hot planets in orbits close to their star. Finally, we cannot fail to mention the Laser Interferometer Space Antenna, or LISA, which is perhaps the most ambitious space telescope project currently in the design or construction phase. And to be honest, it might not even be appropriate to call it a true telescope, at least not in the conventional sense of the term. LISA is indeed a space mission designed to detect and accurately measure gravitational waves, i.e., ripples in the fabric of space-time caused by the movement of large masses in the universe. LISA will be the first gravitational wave observatory to use laser interferometry, which will be placed in space. The concept of the project involves a constellation of 3 satellites arranged in an equilateral triangle with sides 2.5 million kilometers long. These 3 satellites will fly along a heliocentric orbit similar to that of Earth. The distance between the satellites is monitored with extreme precision and also maintained with extreme precision so that, upon the passage of a gravitational wave, the length of the laser beams connecting the 3 satellites is altered, thus allowing this gravitational event to be detected. The LISA project began as a joint effort between NASA and ESA, but the American agency later withdrew from its realization due to budget issues. However, on January 25, 2024, the LISA mission was confirmed by the European Space Agency. The launch of the 3 satellites that will then compose the LISA Observatory is currently scheduled for 2035, also aboard an Ariane 6. All the projects we have discussed are ambitious, costly, but also very fascinating and important because they will push forward our ability to observe, study, and analyze the mysteries of the universe. And there is nothing more important than understanding our universe to understand ourselves a little better and the role of humanity on Earth. As for telescopes under design, there are many others. On Earth, for example, the Einstein telescope, or ET, is currently being studied by several entities of the European Union. This future detector of gravitational waves, compared to LIGO and Virgo, will push a bit further. The entire structure of the Einstein telescope will indeed be built underground to mitigate disturbances caused by environmental seismic noise, and the size of the interferometer will move from the 3 or 4 kilometers of LIGO and Virgo to 10 kilometers. In space, meanwhile, we are looking forward to particularly exciting years from various perspectives. One such future mission is the Athena Space Telescope, scheduled for launch in 2035. Athena, an ESA X-ray astrophysics observatory, will study the hottest and most energetic components of the universe. It aims to explore supermassive black holes at the center of galaxies and the processes regulating the formation and evolution of galaxies themselves. This mission is part of ESA's Cosmic Vision program, which seeks to understand the fundamental forces shaping our universe. Indeed, there are many other projects in the pipeline, and in the future, we will push even further with larger and more distant space telescopes. Not to mention the prospects of equipping the far side of the Moon with radio telescopes, an idea that is gaining traction among scientists and could revolutionize radio astronomy, being free from terrestrial interference and offering a new window to observe the primordial universe. The ideas are abundant and the technology to make them real is advancing in leaps and bounds. All that remains is to find the funding and the people with the vision and willingness to realize these enterprises. Thank you for watching this new video. Please leave a like and subscribe to the channel to support us.